The periodic table. It's not just that colorful chart hanging in a chemistry classroom, it's basically a map to the entire universe of matter. But what if I told you that all the wildly different behaviors of every single element, from the metal in your phone to the very air you're breathing, can all be explained by one single underlying force? Well, today, we're cracking that code.
I mean, really think about it for a second. Why is gold, well, gold, solid and shiny, while oxygen is just an invisible gas? Why do some elements react, let's say, explosively, while others just sit there and do nothing at all? It looks like a whole lot of chaos, but it's actually an incredibly elegant system. And by the end of this, you're going to see exactly how it all clicks into place.
So here's our game plan. We're going to start with the fundamental tug-of-war that's happening inside every atom. Then, we'll see how that little battle determines an atom's size, what it costs to snatch one of its electrons, and how badly it wants to grab electrons from other atoms. And finally, we'll put the whole thing together and see how we can actually predict what an element is going to do.
All right, to understand the whole table, we've got to start small, like impossibly small. We need to zoom right into a single atom, where there's this constant battle going on between the positive nucleus in the center and its cloud of negative electrons buzzing around it.
So let's talk about this idea of screening. Imagine the nucleus is a giant speaker at a concert, blasting out this positive charge. The outermost electrons, the ones on the edge of the crowd, are trying to hear it. But you've got all these other inner electrons in the way. They're like the people in front of you, blocking the sound, pushing back, and basically shielding the outer guys from feeling the full pull of the nucleus.
And here's the key takeaway. Those outermost electrons, they don't feel the full raw power of the nucleus. They feel a reduced pull, and there's a name for this: effective nuclear charge, or, as you'll hear me say a lot, ZEF. It's pretty simple, really. It's the total nuclear charge, Z, minus that screening effect, sigma. This ZEF, this is the actual grip the nucleus has on its most important electrons.
And folks, that's it. That is the secret code, ZEF. This one number, this net pulling force, is the key that unlocks pretty much all the major trends and behaviors we see across the entire periodic table. Let me show you how.
Okay, so the first and most direct consequence of ZEF is something really simple: the physical size of the atom. You can think of it as the first domino to fall. Once you understand this, everything else just follows in a nice, predictable pattern.
So, how does this actually play out on the table? Well, as you go from left to right across a row, you're adding more protons to the nucleus, right? So the pull gets stronger. But you're adding the new electrons to the same outer shell, so they're not very good at shielding each other. The result? ZEF goes up, that electron cloud gets pulled in tighter, and the atoms actually get smaller. Kind of weird, huh? But then, when you go down a column, you're adding whole new layers of electrons, making the atom bigger, just like adding another layer to an onion.
And what's so cool is that even the weird exceptions actually prove the rule. See, it turns out that electrons in d and f orbitals are just terrible at screening. They're really bad at it. So as you fill those up in the transition metals, ZF shoots up more than you'd expect, and the atoms shrink. The most famous example is the lanthanide contraction, where the awful screening by the 4f electrons makes hafnium, which is right below zirconium, almost the exact same size. It all comes back to ZF.
Okay, so ZEF tells us how tightly the nucleus holds onto its electrons. It makes sense then that it also determines the price you have to pay to take one of those electrons away. And that price has a name: ionization enthalpy.
Put simply, ionization enthalpy is just the energy it costs to pluck off an atom's outermost electron. Think of it like this: if an atom has a high ZEF, that's a really tight grip, so the price to remove that electron is gonna be high. If the ZEF is low, the grip is loose, and the price is cheap. It's totally logical.
And of course, it's a price that keeps going up. Once you remove one electron, what's left behind is now a positive ion. That nucleus now has an even tighter grip on the fewer electrons that remain, so removing a second one costs even more energy, and a third, even more, and so on. Now, you'd think this would just be a nice, smooth increase, but chemistry, it loves a good plot twist.
And this is where it gets really interesting. In general, as ZEF increases across the row, the ionization energy should also go up. But look at what actually happens. You see these little swaps. Beryllium and boron are flipped, and so are nitrogen and oxygen. Why? It all comes down to stability. Beryllium has a full 2s subshell, and nitrogen has a 2p subshell that's exactly half full. These specific arrangements are extra stable, kind of like a perfectly balanced stack of books. The atom is just happy where it is, and it makes you pay a little extra to mess that up.
So we know the cost to remove an electron, but what about an atom's desire to gain one? This brings us to a couple of new ideas that, you guessed it, are all controlled by the pull of Zeph.
Electron gain enthalpy is basically the energy change that happens when an atom accepts a brand new electron. For most elements, this is a great deal. They've got room, they've got a strong Zeph to pull it in, so they actually release energy in the process. But for atoms that are already perfectly stable, like your noble gases, forcing another electron onto them actually costs energy. They have zero interest. Thank you very much.
Now you have to see this, because it's one of the most famous little quirks in all of chemistry. You would think fluorine, the king of pulling on electrons, would be the most excited to gain a new one. But it's actually chlorine, right below it, that has a higher affinity. Why on earth? Well, fluorine is just too small. Its electrons are crammed into such a tiny space, it's like trying to shove one more person into an already packed phone booth. The new electron feels a ton of repulsion. Chlorine is a bit bigger. There's more elbow room, so it's actually a little more welcoming.
And finally, we get to electronegativity. You can think of this as the ultimate summary of an atom's pulling power. When two atoms are sharing electrons in a chemical bond, the one with the higher electronegativity is going to win that tug of war and pull the shared electrons closer to itself. It's the direct result of having a high Zeph and a nice small size. Okay, so we've cracked the code. We get Z effect. We know how it affects size, ionization energy, and electronegativity. So what? Well, now comes the fun part. We can stop just describing what the table looks like and start using it to make some really powerful predictions. For example, check this out. If I just give you a list of the successive ionization energies for some mystery element, you can tell me its valence, which is how it's going to bond with other atoms. All you do is look for the first huge jump in energy. That massive price hike happens when you try to rip an electron from a stable inner core shell. So the number of electrons you manage to pull off before that giant leap, that's your number of valence electrons. It's that simple.
And this brings us right back to our original question about gold versus oxygen. What does it really mean to be a metal? Well, chemically, it means you give up electrons easily. So it makes perfect sense. Elements with a low ionization energy, a cheap price to lose an electron, are going to be your most metallic and reactive elements. See? It all connects.
All right, let's put it all together. Quick-fire round. First up, ions of the same element. Look what happens as you go from a negative ion on the left, which has extra electrons, to a positive one on the right, which has lost electrons. The effective nuclear charge felt by those remaining electrons goes way up. And the result? The ion shrinks, and bam, all those properties related to pulling power, ionization energy, electron affinity, and electronegativity, they all go up too.
And here's the kicker. That exact same rule holds true even when you're looking at completely different elements, as long as they happen to have the same number of electrons. As the true nuclear charge, Z, increases across the series, ZF goes up and you see the exact same pattern. Size goes down and all the pulling power properties go up. It's the Zepf principle and it works everywhere. So the periodic table isn't just a random collection of facts after all, is it? It's a system. A beautiful, predictable set of rules that all stem from one core idea, that effective nuclear charge. And it leaves us with a really fascinating thought. If we understand these rules so well, if it's all this predictable, could we one day move beyond just discovering new elements and actually start designing them with the exact properties we need?